Our next topic in chapter 2 is momentum and impulse. Momentum and impulse are also physical quantities that are frequently used in physics, and they are one of the fundamental physical quantities. Momentum is defined as a measure of an object's motion. Measure of an object's motion. What that means is that if an object has larger momentum, then if you try to stop it from its motion to rest position, then it will be harder, and if the momentum is less, then it will be easier to stop the object from motion. And the momentum is defined in terms of its mass and velocity. And when we write mathematically, generally we use a symbol P for momentum, and mathematically it can be written as velocity is equals to mass times velocity. The unit is mass is kilogram, velocity is meter per second, so the unit of momentum is kg meter per second. And one thing we need to remember is that this velocity is a vector quantity, and the momentum depends on velocity. That means momentum is also a vector quantity. What that means is that momentum will depend on both direction as well as magnitude of the velocity. For example, a car moving at 20 meter per second has a different momentum than a car that is moving west at same velocity. We can also see an example here to observe the effect of mass and velocity. We have first case, we have an object move with a mass of 7 kilogram and moving at 2 meter per second velocity, which is pretty small compared to a second mass, which is 0.07 kilograms, but moving at very large speed of 200 meter per second. And if you calculate the moment is the ratio of the momentum is the ratio of mass time velocity. And if you see here, this is 7 times 2, which is 14 kg meter per second. And in the second case, the mass is reduced, however velocity is increased, and overall we have the same momentum, meaning even the first object is very large compared to the second object. If they are in motion and we want to stop them, we will have to put in same amount of effort for both objects regardless of their size or the velocity, because the overall their momentum is the same. And we have an example here of a rifle firing to show a conservation of momentum. What conservation of momentum states is that the momentum of a system will remain constant, total momentum. So the conservation of momentum is basically saying that the momentum will conserve within a system. In other words, total momentum remains constant. For example, here we have a rifle and a bullet. Initially, before being fired, a rifle and a bullet have a total momentum of, so the initial momentum P is equals to mv, and since the bullet is not fired yet, the mass is what will be the mass? Mass will be uh, rifle plus mass of bullet and velocity, where velocity is equals to 0 because it's not fired yet, so initial velocity is 0. And so before being fired, the rifle and the bullet have a total momentum of 0, and when we fire the rifle, the bullet is then propelled in one direction with a forward momentum of mv, uh, mv, yeah, with the mass of a bullet and the velocity of a bullet. And at the same time, the bullet will also recoil in the opposite direction to bullet, and the momentum is given by mass of sorry, not bullet, rifle. The rifle will recoil opposite to the direction of bullet, and the momentum of the recoil is given by mass of rifle times velocity of rifle. And what did we say when we started the top this slide is that momentum is conserved within a system. That means the initial momentum of the system is equals to final momentum. And we know the initial velocity was 0, so initially the system was at rest, so there was no momentum, so initial momentum is equals to momentum is 0, and the final momentum is momentum of bullet, mv bullet, plus momentum of rifle. But we should note that the rifle is recoiling in opposite direction, so it should be negative br. So we get our recoil in term of negative momentum compared to the bullet, but because of the conservation of momentum, the magnitude of the momentum for bullet and rifle is the same. And we can simplify this conservation of momentum for general case where we have two masses, mass 1 and mass 2. The initial momentum of the total system is the initial momentum of mass 1 and initial momentum of mass 2, and the final momentum of the system is uh, final momentum of mass 1 plus final momentum of mass 2. Here we have mass 1 was initially moving at initial velocity of v1i, and mass 1 will move at final velocity v1f after they collide with each other, after they interact with each other. And in the second case, the velocity is initial velocity of mass 2 is v2i, and final velocity of mass 2 is v2f. And mathematically we can combine these two here, and the first term is total initial momentum, and the second term is total final momentum. Initial momentum is basically the mass at the initial case times corresponding velocity, corresponding initial velocity, and final momentum is mass times corresponding final velocity. let's look at a mathematical example. A 20 kilogram railroad car is coasting at 3 meter per second when it collides and couples with a second identical car at rest. What is the resulting speed of combined cars? So what this problem is asking us is that we need to find the mass of the velocity of a coupled car. So we have one car initially moving at mass of car is 20,000 and it's moving at 3 meter per second, and we also have a second car and it also says it's an identical car. So this is car 1, car 2, mass is the same, m2 is equals to m1, and initial velocity of this car is 0 because it says that the car is at rest. And one more thing is that the question also mentions after the collision two cars will couple and form a single car, that is m will be m1 plus m2. Since these two cars are coupled as one car, then we will have only one velocity because both cars will move at the same speed because they are coupled together. So if this is the case, then we can simplify our equation, like conservation of momentum equation from here, right? And from the initial case, what do we know? The second car is at rest, right? So m1 v1 initial plus 0 because we don't have a momentum for the second car initially because it's at rest. And what happens in the second case? These two masses are combined together and they are moving with a same velocity, right? So the final momentum of both objects will be m1 plus m2 as a mass, and they will be moving at the same velocity v. Now what is the initial momentum? The mass of the car 1 is 20,000 and it's moving at 3 meters, 20,000 kilogram, and it's moving at 3 meter per second is equals to, and total mass is 20,000 of car 1, 20,000 of car 2 kilogram, and velocity bf, and we are required to calculate the velocity, the final velocity of the coupled car. So this is 60,000 kilogram meter per second is equals to 40,000 kilogram bf. Now we need to calculate this bf. So if we isolate bf, we have 60,000 over 40,000, and the unit here is kg meter per second, and for the second case is kg. Kg cancels out, and if we divide 60,000 by 40,000, we will get 1.5 meter per second. So the final velocity is 1.5 meter per second. After the collision, two cars will couple together and move at 1.5 meter per second velocity. Now let's talk about impulse. Impulse is an effect which is observed when observed when two objects collide with each other for a short period of time. Or, in other words, our impulse is a force acting on an object for short amount of time. So, for example, when two objects are colliding, the time period between their interaction is very small, and we call it impulse. And what impulse does is impulse changes the momentum. For example, if we have objects m1 and m2, they're moving toward each other, and once they collide, they may go back to the opposite direction. Or sometimes if you have a different mass ratio, this may, after collision, this may go. So this is initial, and we may have different case. The first case is both masses are moving in opposite direction now. In other case, one of the mass will still remain in the same direction, and other mass may move to opposite direction. Or in other case, it can be reversed. Or in some cases, like we just look at before, mass when there's a collision, these objects may combine together and move as a single mass. And the application of impulse are in different cases, because impulse is felt for a very short amount of time. The same amount of force when under impulse has a higher uh, destructive property. So different different devices like this, earbags, padding elbows, knees protective devices are created for to observe this to negate the effect of impulse. And we can mathematically impulse is defined as change in momentum. So if you remember from Newton's second law of motion, what do we know? Force is equals to mass times acceleration. And what is acceleration? Acceleration is rate of change of velocity, right? So if the v2 is final velocity, v1 is initial velocity, then rate of change is divided by time. Now if we move this delta t in the other side, f delta t is equals to m v2 minus v1. And if you see here, this is nothing but m v2, which is momentum, and m v1, which is also momentum. So this is p2 minus p1. Therefore f is delta t is equals to change in momentum. And this f delta t is what's called impulse. This term is called impulse, and this term is change in momentum. And we should also note that larger time of actions leads to decreased stopping force, because we said the stopping force is related to change in momentum, right? So if delta t is increased, then if you look at this ratio, the change in momentum will decrease, resulting in smaller force required to stop the motion of object. Now let's look at a case here. We have uh, two cases. Case 1, we have a ball moving at initial velocity of 10 meter per second and it's moving towards this wall, and once it hits the wall it bounces back with a final velocity of 5 meter per second. And in case 2, we have an initial velocity, the ball is moving at an initial velocity of 30 meter per second, and once it collides with the wall it bounces back with 20 meter per second speed. And we have to answer these four conceptual questions. And the first is greatest velocity change. Which case will have the greatest velocity change? So we know that velocity is a vector quantity, and in the first case velocity is vector. In the first case initial velocity is 10 meter per second and the final velocity is 5 meter per second, right? So change in velocity is 5. And sorry, so we should also note the direction. So for example, let's assume this direction is positive and this direction is negative. Then in first case initial velocity is 10 meter per second, final velocity is minus 5 meter per second, and change in velocity delta v is equals to final velocity minus initial velocity, which is minus 15 meter per second. And for the second case v1 is 30 meter per second, and it's returning at minus 28 meter per second, and change in velocity is minus 28 meter per second minus 30 meter per second equals to 58 meter per second. So greatest velocity change is case B, and the greatest acceleration is rate of change of velocity, right? And the time period, we do not know the time period, so we will assume the given information is for the same time period. So if you look at this change in velocity for the same time period, in the first case the velocity changed from 10 meter per second to minus 5 meter per second, with a total change in velocity of minus 15 meter per second. And in second case the initial velocity of 30 meter per second and changed to minus 28 meter per second, and the change in velocity is minus 58 meter per second. That means the greatest acceleration is in case B. And change in momentum is also the similar case. For the first case we have 10 meter per second times mass. In the initial since it's asking for change, let's do final first. So minus 5 meter per second times mass minus 10 meter per second time mass. So this is minus 15 meter per second into mass. And for the second case this is minus 28 meter per second times mass minus let's use capital M for mass, because the meter and mass is little bit confusing here. mass minus 30 meter per second mass, which is minus 58 meter per second mass. Since the mass of the ball in both cases is the same, this is a bigger number, so greatest momentum change is also case B. And greatest impulse, what do we know? Impulse F delta t is equals to change in momentum, right? So if the change in momentum is greatest in case B, that means the impulse should also be greatest in case B.